Hi there. We will go over the fundamentals of the finite element approach in this video, which engineers should know before diving into computer programming. We will also discuss the different elements and analysis methods that are used by this method and the applicability of each of them. Finally, we will go over some applications. First, let's review the fundamentals of engineering analysis. Any engineering system, including structures, needs to have a mathematical model developed in order to assess how well the system performs under various loading scenarios. There are two methods to describe this. One approach involves using the matrix stiffness method to represent a discrete system, and in this case, the answer can be found by solving a series of algebraic equations. On the other hand, the continuum mechanics approach can be employed, which is the basis of the finite element method, and the solution is derived by solving a sequence of differential equations. Therefore, the matrix stiffness method main methodology is to discretize the structure to a number of nodes that are connected by one-dimensional elements. External forces are being applied at some of these nodes. It is limited in its application to truss and frame structures. Professor Ray Clough of University of California, Berkeley, coined the terminology finite element method in his paper presented at the Second Conference on Electronic Computation in 1960. He summarized the formulation of the in-plane two-dimensional constant strain triangular membrane element. The paper came as a result of collaboration between Berkeley and Boeing to simulate the experimental behavior of wing structures. Well, how then the finite element method works? First, the continuum is idealized as an assemblage of a number of discrete elements connected at the nodes only. Next, we assume a displacement field in the form of polynomials to specify the relationship between the internal displacements of elements and their nodal displacements. The displacement field of a triangular element is demonstrated. This equation can be used to put the polynomials in matrix form. Therefore, we can state that matrix phi multiplied by vector alpha equals the displacement vector delta. Note that the vector alpha of the polynomial's coefficient is unknown and needs to be determined. If we apply at the nodes, then the vector of nodal displacements delta n is expressed in terms of the 6 by 6 matrix A of known coordinates, multiplied by the unknown vector alpha of polynomial's coefficients. Therefore, once the nodal displacements are solved for, we can find the unknown vector alpha from this equation. We have already showed that the vector of displacements delta inside the element is expressed as product of matrix phi and vector alpha. And vector alpha is the product of inverse of matrix A by the nodal displacements delta n. Therefore, the vector of element displacements delta can be expressed of this product, which we'll call it n, by the vector of nodal displacements delta n. The theory of elasticity can now be used to evaluate the strains, as demonstrated by this equation in terms of the displacements u and v. Thus, merely differentiating this equation is all that is required. And if we do that, we obtain a solution in terms of the nodal displacements. Note that the strain displacement transformation matrix B is basically a product of a known matrix by the inverse of matrix A of known coordinates. The constitutive equations as shown in matrix D relate the stresses to strains. The plane stress elastic solution equation for an isotropic material with known Poisson's ratio mu and Young's modulus E is presented here. And this is the constitutive equation for plane strain solution. The stiffness matrix of the plate element is obtained using the principle of virtual displacements. The virtual work done by the external forces is equal to the virtual work done by internal stresses. If we equate the first two equations, we obtain an expression of the plate element stiffness matrix in terms of both the constitutive matrix D and the strain displacement transformation matrix B. Both are known and expressed in terms of the nodal coordinates and material properties. And the integration is over the continuum. Knowing the element stiffness matrix, the next step is to build up the overall structure stiffness matrix for the whole assemblage K sub S, and solve for the nodal displacements. Once the nodal displacements are obtained, displacements, strains and stresses can be calculated inside the element as explained earlier. As shown, this formulation provides strains and stresses at a single location in the element, which is one of its limitations. Professor Irons of Swansea University in the United Kingdom developed the idea of iso-parametric elements to get around this restriction. This formulation allows deformations at any point inside the element to be provided using the interpolation functions h sub I and the natural coordinate systems x sub I and y sub I. In 1963, Professor Melosh of Duke University demonstrated how the principle of the minimum potential might be used to represent the finite element formulation using variational and energy approaches. In 1969, a doctoral student and Professor Lee of the University at Buffalo demonstrated that finite element nodal equations could be constructed and numerically solved using Galerkin's approach. In the 1970s, Professor Zinkiewicz and his colleagues at Swansea University in Wales, UK, used the Galerkin and energy approaches to solve a variety of physical problems in the fields of fluid mechanics, heat transfer, and structural mechanics. They have demonstrated that these techniques are incredibly effective when applied to significant physical problems that can be idealized as differential equations. The elements that are employed in finite element analysis are now covered. To begin, we have the truss element. It is a two-node element that experiences tension or compression from axial loads. It has an axial displacement as its 1 degree of freedom. It is applied to cables and trusses modeling. The beam element is next. It has 6 degrees of freedom and 2 nodes. Rigid end and moment release capabilities are also included. When compared to their corresponding ones utilizing the stiffness matrix approach, this element, and the truss element as well, determine deformations, stresses, and strains within the element rather than merely at the nodes. The two-dimensional solid or plane elements are next. They include 2 and plane translational degrees of freedom at each node. Therefore, no rotations or moments. They include 2 options, either plane stress elements or plane strain elements. Okay, now we would like to distinguish between plane stress and plane strain solid elements. Plane stress is meant a state of stress in which the stresses in the direction perpendicular to the plane of element are equal 0. They are used to model thin plates that are free to move in the direction normal to the plane of the plate. The term plane strain refers to a condition when the strain normal to the plane is 0. Plane strain problems include a slice of a very long solid structure such as dams and retaining walls. Axisymmetric elements are used to model cylindrical structures. To use these elements, both the structure and loading must be axisymmetric. It provides for the stiffness of 1 radian of the structure. Shell elements account for both in-plane and out-of-plane deformations. Therefore, they carry plate bending, shear and membrane loading. Forces are reported per unit length on the midsurface of the element. A plate element is a special case of the shell element. However, plate elements do not account for membrane loading. When shell elements are bent, shear locking may occur when the element edges are unable to bend, creating artificial shear strain. When the thickness over length ratio drops, the element gets extremely stiff and experiences a decrease in overall deflection. To avoid shear locking, it is crucial to choose the element's geometries carefully. Three-dimensional solid elements are also known as brick elements. They include 3 translational degrees of freedom at each node and no rotations. Quadrilateral and tetrahedral solid elements come in several varieties. The most accurate results are typically obtained from the 27-node element. However, because it takes longer to execute analyses than other elements, it is more expensive. In the majority of the analyses, the 20-node element has shown to be efficient. The ratio of the element's longest dimension to its shortest is known as its aspect ratio. It is important to choose these ratios carefully since as they increase, the analysis's precision decreases. Spring elements are used to connect 2 nodes or to attach a node to ground. Forces are calculated in terms of the spring stiffness and the relative deformation between the element end nodes. A damper element provides the same purpose, but the relationship is between relative velocities and damping. We now go over the types of analyses. First, we would like to distinguish between linear and nonlinear static analyses. Usually, the linear static analysis is used with no consideration for geometry or material nonlinearity. In this case, we try to satisfy the finite element equations P equals K delta, where P is the vector of nodal external forces, K is the overall structural stiffness matrix that remains constant throughout the solution. And we solve for U the unknown vector of nodal displacements. Nonlinear static analysis is undertaken iteratively in time steps. In this case, the stiffness matrix is not constant but dependent on the state of stress and the constitutive model relating the stresses to strains. Therefore, the stiffness matrix is the tangential matrix used in each iteration of the solution of the nonlinear problem and changes with each iteration at each time step. Note that K in this equation is the tangent stiffness matrix calculated at the previous iteration of time t plus time step delta t. P is the vector of external nodal forces, F is the vector of nodal forces that correspond to the element stress in the current configuration, and U and delta U are vector of nodal and incremental displacements. The time domain dynamic analyses are employed to assess the structures for seismic loads. The excitation is input in the form of acceleration or displacement time history. Equilibrium of the finite element equations is satisfied at each time step of the excitation time history. There are several algorithms used for time domain dynamic analyses. The 2 most significant ones are Newmark's and Wilson's methods. The analysis can be performed linearly or nonlinearly. It is possible to carry out dynamic analysis in the frequency domain using several techniques. The most significant ones are spectral analysis methods, which are probabilistic methods, usually used to analyze offshore structures to random ocean wave loads. The response spectrum method is recommended by most of the codes to assess the behavior of structures to seismic loads in the linear phase of vibration. Heat transfer analysis can be performed using the finite element approach. Heat flow is equivalent to stress or pressure, conductivity is equivalent to modulus of elasticity, and temperature is comparable to displacements in structural analysis. In the framework of fluid dynamics, the fluid flow must meet the requirements of mass, momentum, and energy conservation. Therefore, the flow is represented in terms of the Navier-Stokes (NS) equations, a set of partial differential equations. The finite element method is used to discretize the fluid medium to several nodes, by using the continuum approach in computational fluid dynamics and understanding the constitutive relationship of the flow. The Navier-Stokes equations for the continuum are solved numerically by approximating the partial differential equations through a sequence of algebraic equations that the computer solves by adding pertinent boundary and initial conditions. We illustrate some applications of finite element method. Orthotropic decks are usually used for new long-span bridges such as suspension and cable-stayed bridges, or for the replacement of outdated decks on existing bridges. They include several details that need to be designed for cyclic fatigue stresses. Local three-dimensional finite element modeling has been used to thoroughly examine the connection between the longitudinal ribs and the horizontal diaphragms or floor beam, ensuring that the stress range at this connection is within the nominal fatigue resistance. The design of a cable-stayed bridge's pylon in a seismic region included installation of sacrificial link elements within the pylon to yield undamage during a potential earthquake and safeguard the pylons from damage. Thorough testing was done during the design and optimization of these link parts under cyclic drifts, which could advance by up to 0.10 radians. Finite element modeling was used to conduct the experiments, which greatly reduced the amount of time needed to set up a lab experiment for this purpose. The connection elements' cyclic behavior and the development of plasticity are demonstrated. This is barrier gate that fractured during Storm Sandy when wind speed exceeded 70 miles per hour. The barrier is made of pipe aluminum pipe sections. This is the barrier gate before failure. And here is after failure. This is a close-up of the fractured region, where the smaller diameter pipe failed between 0.15 and 0.25 inches from the weld. To demonstrate that the gate section was not designed to sustain this level of wind load, a three-dimensional finite element model was developed using 0.2-inch 3-node shell elements, and the analysis was undertaken for wind load of 70 miles per hour. The weld material was also represented in the model. The analysis demonstrated that the plastic strain reached the ultimate value at the row of elements right above the weld, which is approximately 0.15 to 0.20 inches from the weld. The ultimate plastic strain reached was an indication of failure. Complex bridges have had their seismic design assessed using finite element modeling. The suspension bridge model shown constitutes frame elements for the superstructure, truss elements for the cables and suspenders, and spring elements for the soil structure interaction at the piers and anchorages. At the pier and anchorage foundations, the bridge was subjected to displacement time histories of the near-field incoherent ground motions. Amplified movement of the structure under earthquake excitation is depicted in the video. Time histories of the responses of all the bridge components and connections were post-processed to make sure that the behavior complied with the performance-based design criteria for the bridge and was within allowable bounds. The evaluation of foundation behavior and soil structure interaction issues for large caissons and pile cap groups have also been handled using finite element methods. In one example, the finite element method was employed to ensure that the pile groups and cap are capacity-protected members under the seismic design displacement. In another example, it was used to assess rocking of a large caisson under the seismic design ground motion. In a third example, the stresses inside pipe piles under various drift levels were evaluated using the finite element approach. Basic principles of computational fluid dynamics as implemented in the finite element method were employed to evaluate the distribution of wind pressures on radome structures that are located on top of airport control towers to protect radar equipment. For this purpose, the finite element method was used to simulate a boundary layer that includes the radome as located on top of the control tower. The control tower and its adjacent structures were included in the computational fluid dynamics finite element wind analysis study. The wind computational flow domain employed was 2,000 feet long, 1,000 feet wide, and 358.6 feet high. Design wind velocity of 150 miles per hour was used at the radome base. Finite element wind tunnel are post-processed. This graphic depicts the velocity vectors of the wind approaching the tower in feet per second. It is observed that the greatest values are shown to be on the radome. The turbulence kinetic energy is the parameter that indicates the turbulence in the flow. The higher the value of turbulence kinetic energy, the higher the flow turbulence content in the region. This graphic depicts the distribution of turbulence kinetic energy in the flow domain represented by the model. It is shown that the maximum values exist near the rear face of the tower and radome and the downstream of the flow. The high value in the downstream is attributed to the circulation of air behind the tower as a result of the interaction of the wind flow in both the tower and radome. The figure on the right depicts the distribution of wind pressures on the radome. The wind pressures as obtained from the computational fluid dynamics analysis are applied to the radome structure in a subsequent finite element stress analysis to estimate the maximum principal stresses, which are shown in the figure on the left. Our video comes to an end here. Please give us a thumbs up and subscribe to the channel if you enjoy it.